Have you ever really stopped and wondered how AI like ChatGPT actually works? I mean, how a machine went from being a calculator to something that can write a poem or even have a conversation? Well, today we are pulling back the curtain on the secret origin story of the AI revolution. We're going to find out exactly how computers learned to understand our language.
Okay, let's just start with the most basic question of all. Look at this sentence. When you and I see it, we see words, we see meaning. But a computer? It sees, well, not much. Deep down, a computer only gets one thing: numbers. So the fundamental puzzle we have to solve is, how do you turn human language into pure math? That's the whole game.
All right, so our first step on this whole journey is all about deconstruction. We've got to figure out how to chop up language into little, bite-sized pieces that a computer can actually handle. This is the absolute foundation for everything that comes next.
And this process, it has a name. It's called tokenization. Honestly, the best way to think about it is like you're dicing up vegetables before you start cooking. You can't just throw a whole onion in the pot, right? You have to break it down into smaller, manageable units. And in our case, those units are called tokens.
Now, there are a few ways to do this dicing. The early simple way was just to split a sentence by its words. Easy enough, but it has a huge flaw. The model would see the word run and the word runs as two completely different unrelated things. A much smarter way is subword tokenization. This method is clever enough to see that both words share the same root, run, which is absolutely critical for understanding how language actually works.
Okay, so we've diced up our sentence into a list of tokens, and we've given each one a number. But right now, they're just labels, kind of like jersey numbers on a football team. Number 12 isn't inherently better than number 87. It's just an ID. So the next big puzzle is, how do we make these numbers actually represent meaning?
Well, one of the first stabs at this was a method called one-hot encoding. Just imagine you have a dictionary with, say, 10,000 words. For any given token, you'd create this massive list of 10,000 zeros, and you just flip one of them to a 1 at the position that matches your word.
And this is where that idea totally falls apart. Because of how the math works, the similarity between Teddy and bear is 0, but the similarity between Teddy and book is also 0. As far as the model is concerned, a teddy bear is just as unrelated to a bear as it is to a book, which is, useless.
And that's the killer flaw, right? This method gives the model absolutely zero insight into how words relate to each other. It's like having a dictionary with no definitions, just a long list of words. This was a massive, massive roadblock for AI.
And then came the breakthrough, a brilliant idea called word embeddings. Instead of that simple on or off switch, this technique gives each token a whole list, a vector of numbers. You can think of it like creating a giant, multi-dimensional map of language, where words that have similar meanings are placed close to each other, like neighbors in a city.
And here's the classic example that just blew everyone's mind. If you take the number vector for king, subtract the vector for man, and add the vector for woman, the resulting vector you get is incredibly close to the one for queen. This was insane. It proved that embeddings didn't just capture simple similarity, they captured complex, abstract relationships.
So this is huge. Now our AI understands what individual words mean and how they relate. But we've just run into our next big problem. A sentence isn't just a bag of words you can shake up. The order, the grammar, the context, that's everything. A riverbank is a very different thing from a bank robbery.
The first real attempt to crack this context problem was a type of model called a recurrent neural network, or an RNN for short. And the logic behind it made a lot of sense. It tried to act like a human, reading the sentence one word at a time and carrying a little bit of memory from one word to the next.
So an RNN would read the, then bear, then which, then had, and so on, trying to update its memory with each step. But this one-by-one process, it turns out, has a critical weakness, especially in a long sentence like this one.
Just think about it. By the time the model gets all the way to the end and sees the word roared, has it forgotten what the sentence was even about? Has that initial crucial piece of information, the bear, just faded away? Well, in a lot of cases, yeah, it had.
This has a technical name, the vanishing gradient problem. But all it really means is that the influence of the early words gets weaker and weaker with every new word it reads. The model basically had a really bad short-term memory, and this was a huge barrier to understanding anything complex.
But then,
Everything changed. In 2017, a research paper was published with a revolutionary idea that didn't just solve this memory problem, it completely changed the entire field of AI and paved the way for the world we live in today.
It all came from this one paper, and honestly, it has one of the best, most confident titles in the history of computer science. Attention is all you need. And that title says it all. The authors basically said, you don't need better memory, you need a whole new way of looking at the problem.
So what is attention? Well, instead of that slow, one-word-at-a-time process, the attention mechanism lets the model see the entire sentence all at once. It creates direct connections between every single word and every other word, so it can weigh the importance of each one no matter how far apart they are.
Okay, here's a really simple way to wrap your head around it. Say we're trying to understand the word slept. That's our query. The model looks at all the other words in the sentence. Let's call them the keys to find clues. It sees the key bear and realizes, aha, that's a very relevant clue. So it grabs the meaning or the value of the word bear and uses it to update its understanding of slept. It now knows we're talking about an animal sleeping, not a computer in sleep mode. And this powerful, game-changing attention mechanism became the core engine for an entirely new kind of AI architecture, an architecture that now dominates the entire field. And that architecture is, of course, the transformer. In a nutshell, it has two key parts. First, the encoder reads your input, your question, and uses self-attention to figure out how all the words in that question relate to each other. Then the decoder gets to work generating the answer, using cross-attention to constantly look back and pay attention to the most important parts of the question it just read.
And that's it. That's the blueprint. This whole stack, tokenization, word embeddings, and the attention mechanism inside the transformer is the fundamental building block of every single modern large language model you've ever heard of, from ChatGPT to Gemini and all the others.
I mean, just look at this chart. The shift wasn't a gradual evolution, it was a hostile takeover. The transformer architecture didn't just improve on the old methods like RNNs, it made them almost completely irrelevant.